Okay.
Okay.
Ready? Okay. So Ilan is the chairman of today, yes?
Okay.
Mhm.
So it's my pleasure to introduce you, Professor Bernardo Llano. He's professor and thanks to him, introduced to the world of tournaments. He has obtained great results on diagraphs using
Ilan, no te escuchamos. Creo que se nos fue Ilan, a ver si regresa.
I am here. Sorry. Do you hear me? Okay.
Yes.
So, as I said, I know him several years ago at a conference of the Mexican Mathematical Society, and thanks to him, I was introduced to the world of tournaments. He has obtained great results on diagraphs using additive number theory, and for this occasion, he will talk about graph operators. Thank you, Bernardo, and welcome.
Thank you, everybody. Thank you, the organizing committee, for the invitation. And I want to say that I'm very, very pleased that you rescued this part of 2020 in this very, say, misfortune year or year of many misfortunes. And it is, I really appreciate that you rescued this conference. I think I have been participating in all cards from the beginning, except I think last year, because I was out of Mexico, I was in Argentina. So let me share the talk. Could you see it?
Yes.
Can you see it? Okay. No, let's begin. I will talk about graph operators today. Really, it is a very interesting topic and a very wide topic. And I will be only giving an overview on this type of problems. And really, I will flight over some, just a few operators, because there are a lot of things done in this area. So let's begin. I will define graph operators. Let G be a set of graph or diagraphs, any kind, and a function, or as called in this area, operator, which is just a phi function from G to G. And for example, I will give a lot of examples. We have many kind of operators. The first one is a very well-known thing. This is called the line graph of a graph. Say, here, I have some pictures how to define a line graph of a graph. And for example, I have this F graph here. I denote it by letters A, B, C, D, the edges of the F graph. And then I assigned by the L operator the image graph, which is this one. And you can take this graph by the following operation. For each edge, you put a vertex. Here, this is the A, the B edge, etc. And then you join two of them if the intersection of these two edges is not empty. So they intersect in one vertex, then you put an edge. So you obtain this graph. This is the image of the F graph, and here you can see the very easy example from a path on 5 vertices, and the image a path of 4 vertices is very easy because you have four vertices. I put the vertex just to the same height of the edge. Here is the edge, and here is the corresponding vertex, this one, and it's easy to see that the image is a P4. And for example, for cycles, it is easy to see that for cycles, you have the same image. So this is the first example. You can have the same example if you consider the set of all simple diagraphs. When I say simple diagraph, I mean oriented graphs. We don't allow multiple edges, multiple arcs, loops, any kind of these things. And the rule is very easy. You put a vertex for every arc. Here is the vertex A for the arc A, and this is the vertex for the arc B. And then if the arcs are consecutive I mean that the end of the A arc is the vertex of the beginning of the B arc, then you put an arrow. So this is the operation. Here you have the same example, the oriented path, and the image is the same, and the cycles are again the same image. A cycle of M on M vertices have line diagraph, the cycle of number of vertices. There is a more complicated example. This is from Prisoner's book. In my abstract of the talk, I mentioned the Prisoner's book, which is graph dynamics. And this is a very nice, complicated but nice book. And I have this example from the book. And here you have, for example, if you made this operation from this graph, you obtain that. You can check it. So this is the second operator. We have another one, a very well known, the so-called click graph. When you assign a graph, you have a graph G, and you assign as image the click graph. How do you obtain the click graph? It is very easy. Observe, I have an observation here. This is the same graph. I want to point out that you can have in a graph complete subgraphs. For example, this orange triangle is a complete subgraph, but it's not a click. A click for us is a maximal complete subgraph by inclusion. I mean, for example, this is not a click because there is a bigger complete subgraph, namely this blue one, contained in the orange one. So this is a click because there is not a bigger complete subgraph contained in this blue one. So I will look for the clicks of a graph. For example, in this example, I have this click, this K4 here. I have a key 5 here, yeah, and I have a triangle here and a triangle here. If you put a vertex for this, click one vertex for this, one vertex for this, and one vertex for this, and take the so-called intersection graph, which means that if two clicks intersect in one vertex at least, maybe they could intersect in more, but at least in one vertex, then you put an edge. And for example, in this example, you have the key K4. Look, this is one vertex here, one vertex here, one vertex here, one vertex here. And then you check the adjacencies and you have a K4. And of course, if you apply again the operator, which we will be doing that a little later, you get a vertex because it's a click graph. Complete graph, and the image of a complete graph is a click. It's a this is the click graph, which has been studied for a long time, and we have a lot of results, problems, everything. And for example, I give you a very famous example because this is almost the beginning of the study of convergence problems. I will mention later. And this is the very famous, this is the octahedron graph. You pick the octahedron in 3 dimensions, and then you draw a planar representation of this graph. This is octahedron. And of course, you can see, you can see that the octahedron is a K6, a complete graph on 6 vertices. And if you put these pointed edges, you complete a K6 complete graph. And then you can see that really the octahedron graph is a K6 dilating perfect matching. This is the perfect matching of K6, and you obtain that. And you can see it as the 3 copies of K2, 3 copies of 3 edges, and take the complement. For example, it is well depicted here because we have this perfect matching here, and 3 copies of K2, and we take the complement, the graph complement. So, you can prove, it is easy to prove that K of O3 is O4. O4 is, following the same idea, is K8 dilating a perfect matching, and you can see that the 4 K2. So, in general, you have that you can define an m-dimensional octahedron, which is a complete graph on 2 m vertices, deleting a perfect matching. You can consider it as m copies of K2, and Victor Neumann proves in the 70s that the big graph of an octahedron on n dimension is another octahedron of dimension 2 to the m minus 1. And this is a very old result. I have the manuscript. I couldn't find for this talk because I wanted to get a photograph of the page when he wrote about this. But this result appeared in this very old paper, which is very nice. It was a proceeding of a congress in France, and it was published in 1978. So there is another operator. I mentioned the line operator, the line graph, the line digraph, the click graph, and now the D-click digraph, which is a little more complicated because the original definition given by Eric Priestner was quite complicated because he defined this operator in a very, very wide class of digraphs, considering loops and considering everything of symmetric edges, mean the edges from both directions, everything. So I will give the definition, and I will give some examples because the examples are very good illustrations for the definition. And for being a little careful, I will say that you have to define a kind of a structure like complete subgraph of a graph. This simplex xy of a subdiagraph G is just a subdiagraph of the original graph, such that you take the vertex set as the union of the two sets. The two sets are different, yes, and you take the arrows like the complete bipartite subgraph. For example, of course, we can have loops, but I don't like to mention now. I will return to this thing with examples, which is very, and we take these simplex, disimplex, which are really some kind of bipartite complete subdiagraphs, and we take the maximal ones, as in the case of cliques, we take the maximal ones, and we say that these are the cliques. For example, there are definitions here. This is one example which illustrates very well the definition. For example, if we take a simple diagraph, observe that you don't have loops, you don't have symmetric arcs. I mean by symmetric arcs from going from one vertex and returning. This is not the case here, and you have disimples. Disimples in this case are, or for example, or arcs is a disample. These 0, 2 to 3. This is a bipartite graph, but they are not maximal by inclusion. The maximal bipartite diagraphs in this case are these one, 0 to 1, 2, 3. These 0, 1, 2, 3, you can see here in the graph. Look at this and this one. Yeah. So they are the maximal, these disimplices. You can have many other disimplices, but they are not maximal. We are only consider the maximal. If you allow loops, and I will talk about this because there are a lot of well, not too many, but some kind of results referring to the class of this graph. When you consider a simple diagraph, but as this the same as the example before, but you put a loop in every vertex like this. This is the same example as before, Joe. I put these loops here. And then the dicliques, the maximal, differs from the original example because you allowed here, for example, look at this diclique. Here, the X set is 0, 1, and the Y set is 1, 2, 3. And this is possible because you have this loop. And then the dicliques, the maximal bipartite graphs, yeah, allows you to have this. This is, I put the draw in the bipartite way, but really it is this arrow. I consider this arrow in two sets. Yeah. So we have two dicliques. It is really difficult at the beginning to realize that the dicliques are this form, but after a while you get accustomed. So I will give examples of and results of in two classes of graph. This class, when you don't allow anything, this is a simple diagraph without loops, and this one. This class, we call this reflexive diagraph. This is a term from Pearson's book, and we will have results on this class which are different from the original. Yeah? It depends on on the classes. So, for example, we can define again the diclic digraph of D, and what we get. For example, we put these, observe, these are the diclics I mentioned before, and then I will put an arrow between two diclics if the end vertices, the end set of the diclic, intersection, the beginning of the set is not empty, as it said. I will put an arrow from a diclic, from a bipartite digraph, from this bipartite digraph. I think I have to put the prime here. Why intersection X prime is not empty. For example, here, these and these are not empty. I put an arrow here, I put an arrow here because the 2 is, I put 1 here, and you can check there is no more arrows. So, as you see, this is a vertex here, this is a vertex here, this is a vertex here, and I have a so-called TT3, or a transitive tournament and an acyclic tournament on 3 vertices. So this is a TT4, transitive tournament on 4 vertices, or equivalently complete or the tournament and a cyclic tournament on 4 vertices. It is easy to prove that these tournaments, you can define TT4, TT5, TTN, so the transitive tournaments on n vertices, is easy to see that they are unique up to isomorphism. There is only one. And there are very well-known objects in tournament theory, and you can see that it's equivalent to a linear ordering, whatever. So you can check it in the literature. It's really easy to find in almost every book. Yeah. Okay, this is the diclic digraph. So, for example, the diclic digraph, in the case you have loops, as before I said, you have 2 diclics, so you have only one arc, and then the image is again digraph with vertices, with loops. This is a TT4, this is a TT2. This is an acyclic tournament with loops on 2 vertices. This is vertex. This vertex is this diclic, this vertex is this diclic. You can check that there is only one arrow from here to here. Could be in some examples, this is not uncommon, that you can have an arrow from this vertex and returning one. But I don't consider these cases in this talk. So this is the diclic graph. Now we are interested in iterating the five operator. What happens if we repeat and repeat and repeat this operator to the image? So I repeat the application of the operator and want to search for the behavior of the graphs. And this is the iteration function, which is a recursive definition. You define the first step to be first one, and the nth iteration is applying phi of g, the step before, phi of to the n minus 1. This is a common definition. And I want to know about what is the behavior of this function. And from the general operator theory, you can define that one operator is, or one graph, or diagraph is divergent by the operator. It's easy. I wrote it the formal definition, but the behavior is the following. You apply the operator and in many ways, because there are many forms to grow the graph, but in this case, when you apply the operator, the number of vertices at some time, maybe from the first iteration, begins to grow. And at the end, you have an infinite growing of the vertices. And you say that this graph is divergent. Otherwise, it's not phi divergent, it will be called phi convergent. I will say that it's periodic if you get the same graph after some iterations. And we say that this graph is periodic of period n. So after n iterations, you get the same graph. Okay, and after these definitions, we can say that a graph or the diagraph is phi convergent, is periodic, or there exists an n such that phi of n of d is periodic. This means sometimes there are many types of behavior, but sometimes you have a graph and it begins to get many steps after you have a G prime graph, and this G prime gets periodic. So you have a graph goes to this G prime after some iterations, and this G prime goes again a cycle, and you have a periodic. You may have a lot of things in this context. For example, again, for the line graph, you can see that the paths are convergent because you can apply and apply and apply n times the L operator, and you get P1 or K1. You have one vertex. And it means that after that, you have the same one vertex, one vertex, one vertex. Okay, this is an example. You can have the F graph if you made some steps. I made here 1, 2, 4 iterations. Of course, it's not a proof, but you can see it is easy because the divergence of the L operator is characterized, I will mention later, but this F graph is divergent because it's, again, when you make the following iteration of this graph, it gets bigger and bigger and bigger and bigger. So F is divergent. Yeah, we say that the cycles are self-line. It means that in the first step, when you apply the line operator, you stay at the same graph. These classes for any operator are very interesting. The self, whatever, line, diagonal, they are very, very interesting, and they're very, they are objects that are widely studied. So this is a self-line, and we have a characterization of the how the operator L behaves. For example, this is a very old result I took, and it says that if you have the set of all connected simple graph, it is for the line operator, then you have that Cn, the cycles, are the only self-line graphs. That means that in this class, or in this set, Cn, the cycles are the only self-line graphs. Then you have the that for every n, you have that Pn is convergent, and it converges to K1, to a point, to a vertex. Then you have that the claw K13 is evidently a cycle on three vertices, and for any other graph, G is L divergent for any other graph of the class except Cn, Pn, and K1, K1, 3. And this was obtained by Van Ruij and Herbert Wilf in the 60s. In the 60s. This is the nice characterization. Of course, there are many other problems, open problems on line graphs. Of course, you can look for the image of the operator. For example, there is a classic result due to Beinecke, Lowell-Beinecke, that you can characterize when a graph is the line graph of another graph. And this is a very famous term, Beinecke's theorem from the 70s, from 1970. And this is very nice. You can find, for example, in Harari's book or anywhere. These theorems, this Beinecke's theorem says that a graph is a line graph of some digraph if it is not an induced graph of 9 types. It's a kind of minor theorem. You, in some way, you don't allow some prohibited subgraphs. And this is nice, a nice proof, everything. And this is, it appears in this paper. Here, derived graphs are just line graphs. In that time, in 1970, the derived graph, line graph, the same terminology. Now, what happens if you go to direct graph of line digraphs? Well, for example, you have that again, the oriented path is L-convergent. It is easy to see if you apply the definition. There is, recall that there you have a vertex for every arrow. Here is a vertex, a vertex, a vertex, and you put an arrow between two vertices if the arrows are consecutive. Then you can see that it goes to K1, to a vertex. So it is L-convergent. Again, the cycles are self-line, in this case, self-die-line. So in the first step, the same digraph is obtained. And here I put an example from Prisoner's book. It's a very nice example of a 4-periodic oriented graph. See, I begin with this graph, this diagraph, and then I put all the steps, and in the fourth one, you have the same. This is a 4-periodic oriented graph. This is really difficult to find n-periodic graphs by operators in general, but here is a nice example. Here I'm cheating, because here you look at these 2 isolated vertices in this step. This is from here. You have a vertex here, yeah, and they are not related, so this is isolated vertex. And from this you have this because you eliminate these vertices, and this is because you have another definition called mortality, whatever, which is in Priest's book, but I didn't want to complicate more. So I didn't include some, say, more technical definitions. But believe me, it is a very nice example. sometimes in many operators, you can't find these examples, n periodic, whatever, oriented graph, diagraph, in some classes. They're really difficult problem. Yeah. Again, we know when a diagraph, yes, from a simple diagraph means that I don't consider loops, multiple arcs, anything. You have really nice behaved diagraphs. And then Weinecke, again in the 60s, he could prove that a diagraph, a simple diagraph, an oriented diagraph, is self-convergent if and only if all its strong components are directed cycles and not two of them are joined by a directed path. For those that don't remember what it is strong component is, but it is easy because we say that the diagraph is strongly connected or strong if between every pair of vertices you have a directed path. Yeah, and a strong diagraph has only one strong component, and if you don't have, or if you have a not strongly connected, not a strong diagraph, then you have many connected components. So you can find it in, for example, in Van Jensen's book on diagrams, Van Jensen's and Gregory Gutin books. And as a corollary, you have that every strong diagraph is L divergent, and the image of L. So what about, can I characterize the when a diagraph is the line diagraph of another diagraph? Yes, it's a series of paper. In this one it began with Weinecke, and after that Saint Firescu in his PhD thesis continues, and they published together a very nice paper in discrete math in 1982 called Connected Diagraphs and Second-order line diagraphs. These things are really finished. Okay, so for example, for the octahedron, we know that the octahedron is K-divergent. This was first resolved by Victor Neumann Lara in the 70s. And for example, this graph is convergent. I presented this example at the beginning of the talk. This graph G is convergent. Of course, you can have K convergency. Yeah. And we have, I mentioned that in the case of the click graph operator, Escalante is very known Mexican mathematician who unfortunately died very young. He wrote a paper, a couple of papers. This is the first one. And he could prove that there are infinitely many finite connected K periodic graph of period n. For this, for the K, for the click graph, you can find kind of periodic. Of course, this problem is difficult when you want to find 2 periodic, 3 periodic, 4 periodic with some additional properties. So this problem is not totally solved with these. You know that they exist, but they can be very hard to find. And I mentioned this because I told you that click graphs have been long time, have been studied for a long time. And I want to mention this paper because it's beautiful, difficult, and that the recognition problem for click graphs is NP-complete. This is a very nice paper, very difficult one. And I have a conjecture because I wanted to give some problems. This is a very easy one. This is from my friends Paco Larrion, Miguel Pizaña, and Rafael Villarroel. I miss here an L, Villarroel. And this is the snap bisphenoid, which is very, very strange name, is K-divergent. This is easy. This snap bisphenoid is a kind of polyhedron, a three-dimensional polyhedron. Here, I get this picture from Wikipedia. This is the picture of the polyhedron. And when you draw the graph in the plane, you have this graph. You have to prove only that this graph is K-divergent. It is not easy. It is not easy. It is the smallest graph known or not known if it is K-divergent. All graphs on A vertices or less, except that, are K-divergent or convergent. Everything is already set except for this example. And it is a very easy problem as usual in combinatorics, but I hope I see after looking of some computational evidence that it's very, very. This problem is already mentioned in a very nice paper called Expansive on Expansive Graph, which is a very nice paper. I forget to write it, but here it is by Paco Larrion, Miguel Pizaña, and Victor Neumann-Lara, and it was published in the European Journal of Combinatorics 10 years ago or something like that, after Victor's death. This is a very nice paper. But in general, I resume this click graph topic, that saying that there is a very wide literature on click graph. It's a long list of papers, books, surveys, and of course a long collection of beautiful open runtime conjecture, which can be very, very hard. There are a lot of unsolved, interesting, beautiful, easily posed problems like this one. Yeah, and finally, I will focus to the diclick diagraph. So, as I said at the beginning, I will consider two classes. The first one is the class of the oriented graph, simple diagraph. We don't consider here loops. And this one, I put this little loop here up to indicate that this is the set of the same kind of this of the graph of class D, but we put in every vertex a loop. So now, what do we have? For example, this is a TT3. I already mentioned that this is an acyclic tournament. This is easy to see that this is in the class D, where graphs are loopless, and you can see very easily seen that you have two diclicks. This one here and this one here. Yeah. So here you have the image, which is and A and R are an arc. This is K, the TT2. And of course, immediately after two applications, two iterations, you have that in general TT3 is convergent. Of course, you can prove that a TTN, if you have a transitive tournament on vertices, of course, it converges in n steps, in n minus 1 steps. It could be normalized. In the case you have loops in every vertex, this is the class with this little sign here. Here is the example. This is the same example, but you put loops in here. You can see that there is only one cyclic in this case. You can see this is the only one. The only that could be cyclics maybe the loops are the loops, but you don't want loops to be cyclics. Remember that in the definition, a dicyclic means a bipartite graph, some way a bipartite graph, and these two sets have to be different. So if you have only this loop, you have only this edge one-to-one, and for us, it not satisfy the definition. Okay, this is the example. In the case here, I put, this is the TT4, this is TT3. Here I pictured draw the cyclics and how they relate. Look, this is an arrow, and then you have this one, and then you have TT2, whatever. In general, we have this. In the case you put loops in every vertex, on every vertex, then again it is K convergent, and it goes 2 by 2. In every step you lose 2 vertices because of the behavior of this type of graphs. In the class of, and now this is why I am mentioning the class with all the loops, because it was analyzed in Prisoner's book, and he put a lot of problems on this class for this operator, and one of them was that you know that for the K arrows dicyclic graph operator, the cycles are self-dicyclic, means that in the first step you obtain a cycle again. It's easy to see, and Prisoner asks about these examples are unique. No, these are not unique, and the first proof it was Selinka, Bogdan Selinka in 2002, and he gave this beautiful example. This is an orientation of the octahedron graph. I call this the orientation 1 because one paper we need another orientation, but in this case, for this talk, this is the only orientation I will consider. Observe, you have this orientation 0 to 2 to 1, 1 to 2 to 3, etc. This orientation, this is a strongly connected graph. It is regular. It is very nice, and you can see that there is an isomorphism from this graph to this graph. This graph, I call it C6 because 6 vertices. You see the isomorphism 0 to 0, 1 to 1. You can see the isomorphism of these two graphs, and this is a circular graph. I don't want to define them formally, but it's easy to see that you can put the vertices in a circumference, and then you have these jumps, and 0 plus 1, you put one arrow here, 0 plus 2, you put this here, and then 1 plus 1 is 2, 1 plus 2 is 3, etc. So you can define these kind of graphs. I exceptionally, because I love circular graphs, circular diagraphs, circular tournaments, I was introduced to this topic by Victor Neumann, which was a very fan of this kind of graphs. In almost all his papers on tournaments, on acyclic connection, on disconnection, on dichromatic number, he proved some beautiful results on circular. So it is the example of Seneca, and we could prove with she will be talking on, I think, on Friday, and we could prove that this family or this example could be extended to all the family. You can imagine Cn1, 2, put 0, 1 to n minus 1, put n vertices on a circumference, and then put 1, 2 arrows, and then rotate these. It's called circulate. They rotate. Observe that this is circular because if you put say here a pin here, then you can spin this graph, or this diagraph, and the 0 in any way, every vertex is going to take the position of any other vertices, and this means that this diagraph is transitive in the sense of the action of the isomorphism. I don't want to enter in this topic. We could generalize that with Paulina. And after that, we began to study this problem again. I didn't put here the loops, because if I put here the loops, this graph is very complicated. So you can imagine that you have a loop in every graph, and this graph is easy. This graph is nice. This is TT4s here, TT4s, and you, in some way, you put they together such that the last arrow of this TT4 is the first arrow of the next one. And you can imagine this from 3 copies of this, and then you close the graph, and or 4, 5, and you have this kind of graph. We call this DM, and these are self-cyclic graphs. It was a beautiful paper that I have with my friends Mariki Frick from South Africa and Rita. We work a lot in this kind. There are more results in this paper, but I just mentioned this one, which is really nice. And we don't know more than self-cyclic graph in this class. The problem is quite difficult. And even we don't know about divergence, we don't know nothing. We know nothing, almost nothing about this class. So to finish the talk, let me compare 2 cases in the class of every vertex as a loop and the class in which not. For example, here we have a semi-regular tournament. This is a tournament of 4 vertices. It is semi-regular. It's not important for this talk. I just say that this, forgetting for a moment of the loops, this tournament is unique. It's the only it's the only tournament on 4 vertices which is strongly connected and semi-regular, whatever. So this is a very nice example. It is called semi-regular sub 4. This is the notation. And in the class of you put every loop here, it is easy to see that it has only 3 die clicks, and you have the image of a C3 with loops. And of course, it's again convergent. Now, what happens if we forget about the loops? If we forget about the loops, the problem is really, really, really difficult, and we have been able to solve the problem. The problem is almost, the paper is almost ready. We call it, it's the second paper on die-click divergence. It will be submitted in some days because we are working in some details of the introduction. We could prove, the proof is really complicated, that any simple diagraph containing as a sub-diagraph this SR4, this one, is K divergent. And in particular, of course, this is K divergent. And the problem is that here, this is the picture we use in our paper. This is the SR4. This is the image. Forget about these alphas and betas because it's used for other purposes in the paper. This is the image. You can iterate it, the second, third, fourth, I think up to the 5, and the images are very nice. You can see a pattern. But after the 4th or the 5th, I don't remember exactly, I think the 5th iteration, the graph or the diagraph in the result is really a mess. It begins to appear some kind of structure, vertices, whatever, that make the problem horrible. So it's not easy to prove that in this class, this is divergent. And this is the big difference. You have that here, it is easy to see that it's convergent. The image is it's a cycle, and here we have a very, we have a couple of papers on this die-click diagraph. This is the second one, and here almost the main part of the paper is the proof that really this diagraph did diverge. It's quite difficult, very interesting. We spent a lot of time thinking about this problem, and it was beautiful to think about that. There were many frustrations. Sometimes we couldn't prove it after a while. So I will finish with this example and some open problems on die-click diagraph. For example, what about periodic diagraphs when you apply the die-click diagraph? We don't know. We don't know. Are there some examples? We don't know anything. We only know about self-die-click. We know some examples, some infinite families, but when you put here a 2 or a 3 or a 4, we don't know. Another big problem is try to characterize the self-die-click graph. Try to characterize the self-click diagraph. Again, it's a very difficult problem. Again, you can ask for NP-complete recognition problem. I hope, I'm pretty sure that this is an NP-complete problem as click divergence, but it will be very hard. There are a lot more problems, but I don't want to make too much. These are very interesting. The first one is really interesting, and you can try examples and try to find something. Right? We don't know. We know nothing about this. Okay? Thank you so much. Obrigado for our Brazilian friends. Thank you, dziękuję, for my Polish friends, and aquí. This is Afrikaans for our South African colleague. Thank you so much.
Thank you very much, Bernardo. It was a very, very nice talk. Professor Top on the chat said that Eric Prisner would be proud of you.
I knew Eric Prisner. Just I began to work in this topic because I was in a conference in Guanajuato, Mexico, many years ago, I think 12, I don't know, many years ago, and Eric Prisner, it was a classic or a conference that it's celebrated here in America, called Latin American Workshop on Clicks of Graphs. And in this edition, I think it was in 2008, I met Professor Prisner, and he gave a beautiful conference on operators. And then I began to study this and this and this. I love this topic because of his talk. So thank you so much. Thank you to Professor Prisner.
So in the chat say that thank you, very nice talk. And Julian, is there any questions on Facebook or in YouTube?
I'm checking, just wait a bit, but I have one question. You have the D-click number, like the click number, being studied? Someone has studied the D-click number or like the relation with some colorings, like
no, this is a very new topic. I think, as far as I know, there was a very old paper by Haralick in the 70s, mentioned this die-click problem. After that, it was forgotten for a long time. Then it was revived by Prisner in his book. And after that, Zelinka's paper appeared. And after that, we began to work with Paulina, with Rita, with Mariki, and now with Marisa in Argentina, with Silvia in Argentina, and with Miguel here. And as far as I know, they are the only papers in this topic. So almost nothing is now on this topic.
Thank you, Bernardo. Rihanna says, thanks, Bernardo, great talk.
Thank you, Rihanna. Thank you, Rihanna. No, she's from South Africa or from Brazil? I'm confused, a little confused.
South Africa.
South Africa. Yes. Thank you, Rihanna. Thank you. Beautiful country, South Africa. We were in South Africa. Loved this.
And I'm checking, since there is a bit of a delay between the broadcast and the live conference. But right now there are no more questions.
This is a talk for motivation, you know. This is for a big audience. Mainly, we have a big audience of students. And this is a motivation because these operators, I only mentioned 4, but there are a lot of operators, but really a lot of operators. You can check in the business book. There's another one which is beautiful. I didn't mention here. This is called the bipartite click operator. defined by Jaime Schwartfitter from Brazil, and my friend Marina Grosshaus from Argentina. And it is beautiful, and it is quite similar to the oriented case, but the results are quite different. When you orient or you direct a graph, problems are very, very hard and quite different from the original graph problems.
We have a few comments. Laura Pastrana says, saludos Bernardo.
Hello.
Excelente plática.
Hola Laura, gracias por venir. Thank you for coming, Laura. She said very good.
And Katy Esquivel, siempre es un placer escuchar sus charlas.
Gracias, thank you. Danke, dziękuję.
Y creo que son todos los comentarios al momento.
Well, thank you, Bernardo.
Muchas gracias, Bernie, muy bonita.
Thank you
Como
for
siempre.
inviting me. And I was very, I wanted to prepare more, but I have a very busy week, not the 2 months, because we are finishing at the university. I have many other commitments, so I have been very these days. Okay, thank you for inviting me.
Thank you, Bernardo.
Pleasure, always.
So, we see tomorrow.
Tomorrow.
And we have an announcement to make. The videos on Friday will be uploaded a bit earlier so that we can finish with the invited speaker conference, and then we finish the event with a little small ceremony or something like that, and a virtual ceremony. So the videos of the contributed talks would be uploaded before the conference of Paulina, and then the conference of Paulina, and then we finish the event. I don't know if there is something missing, I must say. I think not. Well.
Oh.
No. Well then, see you tomorrow.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
We have a job for Bernardo. Remember that all invited speakers have to say goodbye and see you tomorrow in the language, original language. So, Bernardo.
Gracias por venir.
Adiós.
Adiós, hasta luego. Nos vemos mañana a las 10 para ver a nuestra colega brasileña.
Ok, muchas gracias.
Adiós.
En cubano.
En
cubano.
No,
Sí, cubano.
this is all I'm not a Cuban.
Okay.
Oh.
I'm a Mexican.
Okay.
Bye.
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 See you tomorrow, everybody. Thank you,
Hasta
Bernardo.
mañana.
Very nice talk. Bye.
Gracias.